Okay, curvature. Curvature, by definition, remember, curvature is you have to find the arc length parameterization. You got to find t prime of s. You got to do the length. It's this complicated thing that it really just is here, though. That this is the definition of it. But this encodes so much here. It says you got your R of t. Step one, find the arc length parameterization, and that's already a multi-step process. Step two, you got to take a couple derivatives and so on and so forth. It's miserable. In particular, finding the arc length parameterization. That's what we'd like to avoid. Is there a way to do it? Yes. Because on this slide, I've got two formulas that don't involve the arc length parameterization. This first formula says, hey, you're just working with the one that you got, the R of t. This is find R prime of t, scale to length 1. That gives you t of t. And then find t prime of t. It's actually pretty close to the normal vector, right? This is kind of the steps that we did to find the normal vector, except for then we found a way around it. It turns out you can also do it with this cross product along the way. I'm not going to prove both of these, but I will give you a sense of the first one because it's the chain rule. Everything with the arc length parameterization is the chain rule because it's actually just a substitution. The arc length parameterization is you go from S to T to R to the point. It's a composition of functions, so it's all the chain rules. And here's what it is. dt is dt ds times ds dt. This is a chain rule. This is the multivariable vector valued function chain rule. And then I'm just going to immediately take lengths of both sides because this right here, we just need the length of the dt ds. So I'll take the lengths of both sides. Uh, and the right-hand side is a vector times a scalar. And anytime you're taking the length of a scalar, you just need to throw an absolute value on it. So this is going to be dt ds, that's our goal, times ds dt, which is actually always positive because it increases. Uh, just taking the lengths in this scalar multiple scales. Now, I will point out that we know already that ds dt is the speed. And so it equals r prime of t, the length. And so when I just divide both sides by ds dt, what comes up is dt dt, or t prime of t, divided by, well, the length of it, divided by ds dt, or r prime of t, equals kappa, our curvature. And so because the chain rule is the best differentiation rule, the real reason why it's the best differentiation rule is not because I like the formula or things like that, or it's because everything is composition. Everything is, hey, we got this theoretical idea, but we need to do these transformations to do it. How do those all line up and let us compute from the beginning thing? It's all chain rule all the way down. Chain rule tells us, hey, you don't need to actually find the arc length parameterization. You can skip that and get the same answer via the chain rule and then interpret your answer saying, yeah, we did the arc length parameterization. We got this answer. Great. This second one is just basically building off of that. It's some of the stuff from our normal vector kind of things. Uh, and it's actually a really useful one as well because keep in mind, actually finding t prime of t is a pain. This second formula, which really just boils down to stuff that we saw about t prime of t in the normal vectors. That's all it is its normal vector and an, basically the normal component of acceleration. This second formula, it has a cross product. We've practiced cross products. It uses r prime of t. It uses r double prime of t. It uses the length just to divide it, but it does not ever tell you, hey, scale a vector. And that's the thing that really makes our lives difficult is the scale to length 1 and then differentiate. That's the real hard thing. This just says differentiate to find r prime, differentiate to find r double prime. You already found r prime, find its length, you're done. Well, you got to take a cross product. So let's see how that works with this. This is called a twisted cubic here as it wanders through space. Uh, I don't know if I can find the arc length parameterization of this. I'm not convinced I could. I don't think I would succeed. But we're going to find the curvature anyway. Because kappa, the curvature that we're looking for, is r prime of t cross r double prime of t. It's a cross product. Find the length of that vector and divide it by r prime of t cubed. So what do? We find r prime of t. R prime of t is 1, 2t, 3t squared. We find r double prime of t. It's 0, it's 2, it's 6t. Now it turns out if we only wanted to figure out the curvature at 0, 0, 0, first of all, that's a point you're going to need to back up and find the time. That's not too bad. It's just t equals 0. If that were all this question asked, you can now plug in because we are done differentiating. That's all the derivatives we need. Everything else that we need to do is a cross product and a length. You were allowed to plug in t equals 0 and work from there. It's r prime of t is 1, 0, 0. R double prime is 0, 2, 0. And all of a sudden, we're in great shape that you would say, hey, r prime of 0, I'm going to jump into the ijk notation. It's just I. R double prime of 0 equals just 2j. So r prime cross r double prime is 2. I cross j is 2k. And the length of r prime is 1. So kappa at t equals 0 at that point is the numerator's cross product, length 2, because it's 2k, divided by the length of r prime cubed. This is like a circle of radius 1/2. Because it's 1 over 1/2. 1 over the radius. So the reciprocal gives you this. So a circle of radius 1/2, that's how much this is curving at the origin. We'll look at a picture of it in a moment. Now, because we also want it at a general point, which means we need it for a general time, we actually need to do this more general computation. I need to find r prime cross r double prime. I also need to find the length of r prime. That's the easier one to do. Square root of 1 plus 4t squared plus 9t to the fourth. If we were going to go find the arc length parameterization, you would then get to integrate this square root. Have fun. I'll do it my way here. I'm going to find the cross product. I, j, k. R prime is 1, 2t, 3t squared. It's 0, 2, 6t. We're going to add our other columns here, an I and a j. 1 and 0, 2t and 2. And here we go. My I component goes down and right and down and left. What do we get? That is 12t squared minus 6t squared. The j components goes down there and this way. That first one is a 0. We just get a minus 6t. I'm just tracking down where I am here. The k components. That's a 2. That's a 0. This is 6t squared minus 6t, comma 2. Now we just need to find the length. R prime cross R double prime. Not that bad, really. I mean, especially if we don't need to simplify. 36t to the 4 plus 36t squared plus 4. You could factor out a 4 from this if you wanted to. There's my 4. It got square rooted. That's 9t to the 4th plus 9t squared plus 1. That's not going to simplify it in any sort of reasonable, nice way beyond that. And finally, I'm going to take my camera away so we can just write it down. The curvature is that quantity, 2 9t to the 4th plus 9t squared plus 1 divided by r prime's length, 1 plus 4t squared plus 9t to the fourth. Nothing cancels here. We just get this formula. It's lovely. If you plug in t equals 0, you get 2, which is what we'd expect. The advantage of this bottom formula is that it lets you plug in any time you want. So you can plug in t equals 1 and find the curvature of the twisted cubic at the point 1, 1, 1. You can find the curvature anywhere. Let's take a look at it. So we've got here in GeoGebra set up for us our twisted cubic. It is a cubic curve. You can sort of see that when you look at it from this direction, but it's twisted because it sort of curves back into the y direction. And what you can do is you can compute things like the unit tangent direction at any point. And so as I move along this curve, you're always pointing in that unit tangent direction. You can also compute the unit normal direction, which points perpendicular to that. It's sort of where we're curving, and you can see that in this example that n is twisting as you go through that. And then you can compute the curvature, and I have computed the curvature way down here, that at this point it's relatively small, but the curvature is 1.28 at this point A on the curve. And what that means is that the curvature is kind of like a circle. At that point it should be behaving like a circle, and I can actually work out what that circle is and add it in. And what this means is that I've got the circle and I've got the curve, and it's sort of like a tangent circle in the sense of if I zoom in, the circle and the curve very, very nearly match each other. And eventually the curve sort of goes off. I'm going to drop actually the tangent vector in this. I can move to a different point on this circle, and the circle changes its size at various points, and it sort of twists its way through. But still right here, at every point of sort of pseudo-tangency, what you end up is this circle just sort of touching it. And at the particular point that we had, which is right at 0, you end up with a curvature of 2. So that's like a circle of radius 1/2. That tells you at that instant how fast is it curving. And as soon as time moves on, you get a different value as it sort of spirals out and it gets huge. And I have it coming back eventually here. But you can see that this curvature gets very, very small, but it kind of should. If you look at the curve, it gets very straight at some point. And so we get these small circles sort of twisting through. But then as the curve straightens out, it's not curving so much. So like if you just said, hey, you're going to curve like this, but instead of then changing, keep doing the same curve, you're going to circle all the way around, but it'll be a very big circle. That's what we're sort of doing with this type of question here. Okay, let's jump back into our PowerPoint real quick. I just want to give you one more formula that if you're in 2 dimensions here, which means single variable calculus, so you are instead here, you got y equals f of x, which you could always write, by the way, as r of t, just using a parameter t for x, and then the y is always f of x, so in this case f of t. And if you just set this up and you just work your way through these formulations, you actually get to this. That basically says here's what your kappa is in 2D. So you can just compute it that way, which is a fine thing to do. It's relatively straightforward. It's based off of the fact that as you start taking derivatives, it gets pretty quick. By the way, because curvature, we're going to need a 3rd dimension to do the cross product. You just throw a 0 there. And so much of this stuff ends up being 0. It's relatively straightforward. So let's just do one quick calculation from this using that one that we just did. Kappa equals the absolute value of y double prime over the absolute value of 1 plus y prime squared to the 3 halves. That 3 is just the one from our regular curvature formula that hopefully you've got written down, and so on. I want to find the curvature of y equals x squared at the origin, so we'll say y equals x squared, but I need y prime equals 2x. I need y double prime equals 2. And then here we go. Kappa just is 2. That second derivative, absolute value, I should say that at the origin, that means x equals 0. Is what we're doing down in the denominator. We're going to go 1 plus 2 times 0, 2x squared to the 3 halves. This is just 2. It's another one actually where its kappa is this. Now, technically, if you want to find the oscillating circle, to graph it, you need to also find the normal vector. Good news, we're in 2 dimensions. Here's your tangent, here's your normal, pointing that direction. And that normal direction, that normal vector, the principal normal, that's pointing towards the center of the circle. That's why I kept that in here. We've got a kappa of 2. That corresponds to an r of 1/2. And so if you just come in here and you say, hey, here's this point, 0, 1/2, and you graph a circle at that point, that will be your osculating circle. Now that circle, if you really want to do it, you need an x-coordinate of 0 plus 1/2 cosine of t. You need a y-coordinate of 1/2 plus 1/2 sine of t. You stick your radius in front of this cosine and sine. You could also do it in, regular 2D kinds of things, but you can sketch this osculating circle. On the previous example, the twisted cubic, I jumped through a bunch of hoops to make GeoGebra do it because my circle was sort of in an angle, so I had to figure out how GeoGebra graphs circles. I could have done it formulaically if I really worked hard, but I probably would have thrown some linear algebra at it. We're almost done here. That one thing that we can take from this is that you can actually go back to that a of t formula. Remember that we said a, the acceleration is a tangential component times the tangent vector plus a normal component times the normal vector. And a of t, we can already work out what this is. That it turns out it's the second derivative of s. And so that's what I wrote it down here, that it's ds, d squared s, dt squared. But we also have all of our other formulations of it. So it's just c 12.4 for other AT formulas. What I want to focus on though now is the AN, because there's a connection between curvature and this coefficient AN. There kind of should be, because we said back there that the acceleration, which is about how your velocity changes, and that breaks down into 2 components. How your speed is changing, ds dt is speed, and so the derivative of speed is what we've got here. And then this an times the normal vector piece, that is describing how your direction is changing. So it should have something to do with the curvature. Now, we said back then that an is the length of the velocity vector times the length of t prime of t. Now, the length of the velocity vector is the speed is ds dt. That's just directly here. The tangent vector, well, remember one of our formulations of kappa. T prime of t over r prime of t, but both of them lengths. That was one of our formulations of kappa. This is one of the ways you can find the speed. It's not, or the curvature. It's not the best. You put the curvature on the other side, and all of a sudden you get ds dt. We're going to multiply by r prime of t times kappa. And then we're just going to remember that, oh yeah, both of these are the same thing. These are both descriptions of the speed here. And so it's just actually, if you write it this way, it's the speed squared, and you can bring the kappa in front. It's just another formula. It means that now all of a sudden, if you can find kappa, and guess what, we got formulas to find kappa, you can find the normal component. If you found the normal component in a different way, you can do that as well. You just need this ds dt speed piece. So it's just giving us another way to talk about this. One last question. We're going to go into sort of an amusement park here. We got a go-kart driving around a track. We got to figure out what frictional force we need to be able to keep this cart on the track. We don't want it flying off. We don't want to injure any kids or anything like that. Uh, Now, we got a whole bunch of units going on here, and one of the key things that we're going to need is this fact. The frictional force must equal the mass times the normal component of the acceleration, because it's the friction that is going to keep you from sort of sliding out. So that basically says that the answer has to equal AN, the mass times the AN. This is really just because F has to equal the mass times the acceleration, which is the mass times AT times the tangent vector plus the mass times AN times the normal vector. And this is the part that keeps you on the track. This is the part that lets you accelerate and decelerate, sort of in the standards, hit the accelerator, speed up type of thing. And so it just says, what is the length? What is the magnitude of the force you need? Basically, towards the center of the track is MAN. So this is really a question of, can we find these values? Well, the mass is immediate. 360 kilograms, that is a mass. You have to be careful if something's giving you slugs or something like that. Slugs is a mass, pounds is not a mass. You have to divide to get to a mass there. We also need to figure out AN. Well, here we go. MAN is the mass times kappa times ds dt squared. Well, we know kappa because we got a circular racetrack. Kappa is 1 over 12 meters. We know ds dt because that's the speed. It's 60 kilometers per hour. And so we're good. We just have to plug in these numbers, right? Except we got a unit mismatch. We got meters, we got kilometers. You got to convert from one to the other. I'm going to compute everything into meters, and I'm going to convert everything into seconds as well, because that's our standard units for force. We're going to try to put it into meters and seconds and kilograms. So I'm going to take the 60 kilometers per hour, and I'm going to say this is actually 60,000 meters. Divided by 1 hour's 3,600 seconds. This is 50 meters per 3 seconds. That's how fast this cart is going. But once we've done that, once we've aligned our units into a correct, sort of consistent, coherent unit system, we just say, hey, M times AN, the answer, is 360 kilograms times our kappa, 1 over 12, times 50 over 3 squared. It's just the speed squared that you're going. And so this is exactly the calculation that you need. You work this out and you figure out what you get. You get approximately 8333 kilogram meters per second squared. If you actually look at the units, this is kilograms, this is a meter, and this is a meter squared per second squared. Kilogram meter per second squared is what we have. And that is the unit that we call a Newton. So this is just 8,000 some odd newtons, which is a hefty chunk. Your tires had better be pretty good here because you're going pretty quick around a pretty darn small track here. But that's it here. That we've got a bunch of formulas here in this chapter 12. We got a bunch of big ideas, and what I really want you to focus on is, what are the ideas? What are we measuring? What is curvature really trying to get at? That you're trying to say, how fast are you turning, and we had to set a standard speed there. But of course we don't want to compute that because the arc length parameterization is hard to find. So we have all these ways around it that are basically the chain rule. You can work them all out from the chain rule. It's probably not what I would do. I would probably make sure that you have these formulas easily accessible to you. You want to know what they are, which formulas you can use, what things you can get quickly. You certainly want to know how you're going to get the tangent vectors quickly and so on. You want to know a strategy to get you the normal vector. But once you got that, now we can talk about movement through space and understand the intrinsic properties of the path that we take, how the velocity works, and really everything that we've got. That is it for Chapter 12, and that's it for this video. Until the next time I see you, enjoy the math.